This is a schematic diagram of the ripple tank that we use to make these pictures. The tank here is simply a wooden frame in which a plate of glass is mounted. With the glass carefully leveled, the tank is filled with water to about 2 centimeters depth. Light is projected from below by way of the mirror through the glass and water. We see the light focused onto the screen by the water waves, giving a pattern on the screen the same as the water wave pattern in the tank. A single drop of water serves as a point disturbance. The wave travels with equal speeds in all directions, keeping the pattern circular, and the direction of travel is perpendicular to the wavefront. We can create a straight wave by sharply rolling a long straight dowel in the water. Again, note the direction of propagation is perpendicular to the wavefront. It is difficult to make a single sharp, clean wave. You see secondary or minor disturbances which follow along with the principal wave, but they in no way will affect what we are looking at. A straight wave runs into a straight barrier and reflects. At an incident angle of 0 degrees, the reflected angle is also 0. Here, where the wavefront meets the barrier at 35 degrees, the angle of reflection is also 35 degrees. And at 45 degrees, again, the angle of reflection equals the angle of incidence. Indeed, for all positions of the barrier, the angle that the reflected wave makes with the barrier always equals the angle of incidence. Light, when it reflects from a mirror, shows this same behavior. So does sound when it reflects from a smooth barrier. If we consider each small segment of the circular wavefront, here too we find the angle of reflection is equal to the angle of incidence. This time follow the reflection along the upper half of the barrier. There. The reflected wave seems to come from an origin on the other side of the barrier, at a distance behind the barrier which is equal to the distance of the point source in front. This is called the virtual source of the wave. The circular wave reaches the barrier everywhere at the same instant and reflects back to where it came from. Each segment of the circular wave is incident on the barrier at an angle of 0 degrees and is reflected at 0 degrees. we get an artistic yet nondescript effect. As the point source moves along the principal axis toward one of the foci, the pattern becomes better organized. And finally, when the wave is generated at one focus of the ellipse, all portions of the wavefront reflect from the ellipse and arrive simultaneously at the other focus. At a certain point along this axis, the circular wave is reflected as a straight wave. This point is the focus of the parabola. For example, in a searchlight, the lamp is placed in the focus of a parabolic reflector. Compare these reflections from this barrier to those you just saw from the parabolic barrier. Right here, the central portion of the reflected wave is straight, but then only for a short time. Always part of the wavefront has a curved shape. This phenomenon is usually called spherical aberration. The reflection from this circular barrier is never the consistent straight wave which can be obtained from a parabola. Let's take a look again at what the parabolic barrier will do. The reflection is a perfectly straight wave. The straight wave appears to converge on the focus of this parabola, but it happens too quickly to see very clearly. So, in rapid succession, we repeat the straight wave, giving rise to a short wave train. Now it is much easier to see the waves converge on the focal point of the parabola. This barrier could be a radar reflector detecting microwaves, or the parabolic mirror of a large optical telescope. If you were to select a point anywhere on this wave pattern, you would find 17 wavefronts passing that point every second. This is a frequency of 17 cycles per second. Remember, we're seeing this at half speed, so here you really could only count half of 17. Now the frequency has been lowered to 12 cycles per second, and the wavelength is larger. If you observe these waves through a rotating slotted disc, a stroboscope, you can apparently stop the motion of the waves, and you can measure the distance between successive crests, finding the wavelength that's being used. This periodic straight wave has a frequency of 6 cycles per second. And now 12 cycles per second. A transparent plate has been placed in the lower right of the tank so that the water is shallower there than in the rest of the tank. The wave fronts are incident at an angle of 0 degrees on the boundary between the deep and shallow water, and they slow down when they cross that boundary. The velocity of the waves in the shallow water is less than that of the incident waves in the deep water, and the wavelength in the shallow water is shorter than in the deep water, while the frequency remains unchanged. Now the wavefront crosses the boundary at an angle other than 0 degrees, and here too the wavelength and velocity are less in the shallow area. But notice that the change of velocity of the wavefront as it crosses the boundary at an angle results in a change of direction of the wavefront. This phenomenon is what we call refraction. You can even see the waves partially reflected at the boundary and moving up out of the top of the picture. If we increase the angle at which the incident wavefront hits the boundary, the wavefront is bent more. It is refracted more than before. A beam of light passing into a block of glass refracts in the same way. You remember Snell's law describes this phenomenon precisely. You see a black marker placed on the screen, parallel to the wavefronts of the refracted beam. Now the frequency is increasing so that the wavelength is shorter. With the incident angle the same, the wave is refracted less. The refracted wavefront is no longer parallel to the marker. The angle of refraction is different at different frequencies. We see a similar phenomenon when white light is refracted by a prism, producing a rainbow spectrum. The lens-shaped area has an aperture of 10 to 15 wavelengths. Note the concentration of waves, a focusing effect, near the lens. Now the wavelength is decreasing, and the focal region moves farther from the lens. With water waves, the longer wavelengths are refracted more than the short ones. This effect is just the opposite in light, where the shorter wavelength of visible light, that is, blue light, is refracted more than red light. The dispersion of light waves by a lens is called chromatic aberration. Observe the waves just before they hit the lens. They are straight. As they cross the first boundary of the lens, they become slightly concave as you look at it from the right. Then as they cross the second boundary of the lens, they become even more concave. In this instance, the waves move from shallow to deep water, the reverse of what you saw before. This time the area in the lower right of the tank is deeper than in the rest of the tank. The wave fronts are incident at an angle of 0 degrees on the boundary between the shallow and deep water, and both the velocity of the waves and their wavelength increase when they cross that boundary, just like light coming out of water or glass into air. Here, where the wavefront crosses the boundary at an angle, again the wavefront is bent. Only this time the wavefront is bent in the opposite direction from before, since now the refracted waves travel faster than the incident waves. As the incident wavefront hits the boundary at a larger angle, the wavefront is refracted more. And the angle of incidence between the wavefronts and the boundary can be increased to such a value that the refracted waves just skim along parallel to the edge of the boundary. If the angle between the wavefronts and the boundary is increased beyond this critical angle, there is no longer any refraction. No wave is transmitted at all. The entire wave is totally reflected, and the angle of reflection from the boundary is equal to the angle of incidence. Two wave pulses, started at the same time, spread outward at constant speed, forming a symmetrical pattern. Where the crest of one pulse meets the crest of the other, a point of maximum amplitude results, and this point travels outward along this straight line, which is the perpendicular bisector of a line joining the sources. When one pulse originates after the other, the pattern is not symmetrical. Here the point of maximum amplitude travels along this path, which is bent to the right of the perpendicular bisector of the line joining the sources. When the right-hand pulse lags behind the other even more, the path is bent farther to the right. When the delayed pulse is on the right, the path bends to the right. When the delayed pulse is on the left, the path bends to the left. Clearly, when two pulses interfere, it is their relative time of origin which determines the path the maximum amplitude follows. Two pulses are started at the same time. Then, on the right, a second pulse is produced. Both pulses from the right source interfere with the single pulse from the left source. And the result is two paths of maximum amplitude instead of one. Now, both sources produce second pulses simultaneously. And each pulse from one source interferes with each pulse from the other source. The pattern is symmetrical. and there are 3 paths followed by the maximum amplitudes. When pulses are produced at a constant rate, we see a steady pattern of interference. The paths of maximum amplitude are widely separated because there is a considerable delay between successive pairs of pulses. At a higher pulse rate, the paths of maximum amplitude are much closer together because the delay between successive pairs of pulses is much less. The central maximum lies along the perpendicular bisector of a line joining the sources. This maximum is produced, as we have seen, by pulses emitted simultaneously. The central maximum is called the zero-order maximum because there is no delay between the waves producing it. There are other maxima on either side of this zero-order maximum. Look at the one next to it on the right. This maximum is produced by those waves from the right which lag behind the waves from the left by just 1 period of vibration of the sources. It is a first-order maximum. Likewise, the second maximum on the right is produced by the waves from the right which lag the left by 2 periods of vibration. It is a second-order maximum. And so on for the third and fourth order maxima. Then by symmetry, we can identify the different order maxima on the left. These maxima are regions of constructive interference. They are separated by nodal lines, where destructive interference occurs. 2 sources vibrating simultaneously produce a symmetrical pattern with a central maximum. And we say that those sources are vibrating in phase. The marker lies on the central maximum. Starting with the sources in phase, we introduce a gradually increasing phase difference between the 2 sources. The right-hand set of waves lags further and further behind the left-hand set, and the positions of the maxima and nodal lines change. They've shifted to the right. Now there is a nodal line where before there was a maximum. The right-hand set of waves now lags behind the left-hand set by half the period of vibration. We say the vibrators are 180 degrees out of phase. With a continuous change of phase, the radial pattern sweeps about the origin, repeating itself every 360 degrees of phase shift. The pattern of interference created by sources vibrating in phase depends on 2 factors, the wavelength and the separation of the sources. Here, the separation is d and the wavelength lambda. In this symmetrical pattern, the first maximum to the left of the central maximum is here. In order to see how the interference pattern changes as d and lambda are changed, we will keep this mark just where it is now on the screen. Note the separation of the sources. Without changing the wavelength, we double the separation. The mark now lies on the second maximum instead of the first. The ratio of separation to wavelength is twice what it was before. There are more maxima and minima than before. Now, this time without changing the separation of the sources, the frequency is lowered slowly until the wavelength is double its first value. There, the pattern is steady, and again the mark lies on the first maximum. The ratio of the separation to wavelength is the same as it was before. The pattern here is the same as it was when the wavelength and source separation were both just half this value. The numbers of nodal lines and maxima here are the same as the numbers here. The parameter important in determining the number and angular spread of the maxima is the ratio d over lambda, the distance between the sources measured in units of wavelength. Now, as we slowly increase the frequency, the wavelength decreases. The ratio d over lambda is becoming steadily larger. A narrow slit has been placed in the path of advancing straight waves. Each wavefront passing through this narrow slit spreads out in all directions as it emerges from the far side. To explain this wave phenomenon, one can think of each very small portion of the wavefront which passes through the slit as the source of a new wavelet. For example, a source at the right edge of the slit would produce a spherical wavelet like this, and a source at the left edge would produce a wavelet here. Wavefronts from other sources between these extremes would overlap like this. And if there were a row of closely spaced sources across the entire slit, this is how the wave pattern should look. A nearly spherical wavefront, fairly strong in the forward direction, and quite weak or diffuse at the sides. And indeed, we do see that the spherical wavefront on the far side of a narrow slit is strongest in the forward direction and rather diffuse on the sides. Examine each successive wave passing through the slit, each produced by a great number of wavelets spreading out from this narrow slit. This way of thinking of the propagation of waves was first suggested by Huygens about 300 years ago. Thus we call the wavelets Huygens wavelets. If the slit is widened, more Huygens wavelets originate in the slit. Again, the waves are strongest in the forward direction, but they are much more diffuse at the sides. Of more interest, however, the successive wavefronts overlap each other now. Thus, in this region, where the waves overlap, we may expect to find an interference pattern. And we do see an interference pattern. Two nodal lines, a strong maximum between them, and weak maxima outside them. This interference effect is commonly known as single-slit diffraction. As the slit becomes wider, the interference pattern changes. And when the slit is quite wide, the constructive interference of the Huygens wavelets originating across this wide slit begins to produce an advancing straight wave in the forward direction. and the diffraction effects become relatively less significant. The Huygens wavelets originating at adjacent points along the length of a straight wavefront destructively interfere with each other in all directions except the forward direction, producing an advancing straight wave. But where some of the wavelets are stopped by a barrier, they no longer are able to interfere with the rest of the wavelets, and the wavefront bends around the barrier. When the wavelength is decreased, the disturbance behind the barrier is confined to a region closer to the edge, and the barrier casts a sharper shadow. Diffraction occurs at both edges of this obstacle. Here the shadow is fairly sharp. As the wavelength is increased, more and more bending is evident until, with a wavelength approaching the length of the obstacle, the shadow has almost disappeared. When the wavelength is comparable to the size of an obstacle, the incident wave is hardly disturbed, and a circular wave is visible, with the obstacle as its source. This latter phenomenon is usually called scattering. We can obtain two sources vibrating in phase by using two narrow slits placed close together in the path of an advancing straight wave. These produce a pattern in which single-slit diffraction and double-source interference are combined. Because of diffraction, the energy transmitted through each narrow slit is greatest in the forward direction. And where the diffracted waves overlap, interference produces maxima and minima at angles that depend only on the wavelength and the separation of the two slits. Compare this double-slit interference pattern with the pattern produced by two sources. The ratio of source separation to wavelength here is the same as the ratio of slit separation to wavelength here. An interference pattern with light is normally obtained by using two narrow slits in front of a single source. When more narrow slits are added, without changing the wavelength and separation of the slits, we see that the directions of the principal maxima do not change, but they do become stronger. With 8 slits, 8 diffracted waves interfere with each other, producing a strong zero-order beam in the forward direction, and on each side of it, a first-order beam. Because we are very close to this grating, the disturbed region of intersecting waves is very prominent, but it is clear that out of this seeming chaos, orderly wavefronts emerge. We can see at the top of the screen that with the increase in the number of slits, the advancing wave is straight. And in the first-order beams, the wavefronts are also straight. The marker on the upper left of the screen parallels the wavefront of one first-order beam. The directions of propagation of the first-order beams depend on the wavelength and the separation of the slits. Decreasing the wavelength decreases the angles of the first-order beams. In the same way, when light is incident on a diffraction grating, any given wavelength is associated with characteristic angles of transmission. Refraction occurs when waves move straight across a boundary from a shallow to a deep region of the ripple tank. Here the deep water is on the lower right. Note the increase of velocity when the wave front crosses the boundary. It's like light waves traveling from glass into air. Increase in the velocity of the wave fronts as they cross a boundary at an angle greater than 0 results in a shift in the direction of propagation. At a greater incident angle, the wave is refracted even more. The ratio of the sines of the incident and refracted angles equals the ratio of the velocities of the incident and refracted waves. Snell's law is applicable up to a refractive angle of 90 degrees. We can see what happens as this critical condition is approached. Here, the refracted waves are traveling almost parallel to the boundary surface. The refracted waves are just skimming the boundary. The wavefront very nearly perpendicular to the boundary. But at an incident angle only slightly greater, we see no transmitted wave. The entire wave is reflected. The angle of reflection is equal to the angle of incidence. The reflection from this boundary is just the same as from a plane surface. Even though these waves are totally reflected, some of each wave does penetrate a short distance into the second medium. Boundary penetration can be demonstrated by placing a second transparent plate in the tank, with the water depth over it the same as that over the first. Between the two plates, there's a channel of deeper water. With the plates 2 wavelengths apart, the waves still undergo total internal reflection, and there is no apparent transmission across the channel. With the channel narrowed to 1 wavelength, just a trace of disturbance is transmitted across the channel. When the width of the channel is reduced to a half a wavelength, a wave is clearly transmitted across the channel into the second shallow region. It is refracted at each of the boundaries and moves off in the original direction. Some of the incident wave is reflected as before. With a width of a quarter wavelength, very little of the wave is reflected and most transmitted. And when the plates are touching, there is no boundary. As the channel width is increased, the transmitted wave grows rapidly weaker, and the reflected wave stronger. Until beyond a width of about 1 wavelength, the fraction transmitted is negligible, and virtually all of the incident wave is reflected. Here, the deep water acts as a barrier to the oncoming waves, reflecting them. Although the waves are totally reflected, we have in fact seen that they penetrate the barrier a short distance. This phenomenon of barrier penetration is a general property of waves. Whenever waves encounter barriers, penetration occurs. But the amplitude of the waves becomes less and less the farther into the barrier they penetrate. And if the barrier is narrow like this, that portion of the waves which penetrates to the far side of the barrier gets through and is propagated onward. When we consider the wave aspects of particles with respect to this phenomenon of the barrier penetration of waves, we can better understand the passage of material particles through a potential barrier, as happens in the radioactive decay of atomic nuclei. When straight waves are incident upon an obstacle, scattering occurs. And if that obstacle is small, that is, smaller than a wavelength, the incident wave is hardly disturbed, while the obstacle is the center of a weak, periodic circular wave. When straight waves are incident upon a row of small obstacles, here brass pins evenly spaced, the straight waves continue to advance as before, and each obstacle is the source of a scattered wave. These scattered waves interfere in a predictable manner. Interference of the scattered waves from a single row of obstacles always results in a strong wave reflected in a direction such that the angle of reflection equals the angle of incidence. The direction of the reflected wave does not change if the wavelength is altered. A marker has been placed parallel to the reflected wavefronts, and as we change the wavelength, we see that the wavefronts remain parallel to the marker. If the angle of incidence is changed, the angle of reflection is changed by the same amount. Again, the marker is parallel to these wavefronts, and a change of wavelength has no effect on the direction of the reflected wave. The law of reflection is the same as that for a solid barrier. A solid barrier is really an array of scatterers, spaced very close together. Several linear arrays of small scatterers, evenly spaced in parallel rows, form a lattice. Because of the open spacing, each successive row partially reflects and partially transmits the wave that reaches it. At each row, the wave is reflected at an angle equal to the angle of incidence. The reflected waves are in phase when they emerge from the lattice only if they have traveled distances that differ by whole numbers of wavelengths. The condition for a strong reflected wave depends upon the wavelength, the distance between adjacent rows, and the angle of incidence. The condition for maximum reflection is described by Bragg's law. 2d sine theta equals n lambda, where d is the separation between the rows, theta is the angle between the direction of the incident wave and the row. The frequency is increased, thereby changing the wavelength, and no clear reflected wave appears. The waves reflected from successive rows are no longer in phase when they emerge from the lattice. With a further increase of frequency, the wavelength has 1/2 its first value, and again, the reflected waves are all in phase. If we reduce the frequency, increasing the wavelength, we can recover our condition of destructive interference again. Then, leaving the wavelength unchanged, we can alter the angle of incidence by changing the angle of the lattice, thus restoring a strong reflection. For any frequency and spacing, the angles for which strong reflections occur are called the Bragg angles. For this crystal, this angle is a Bragg angle for this frequency, or for any harmonic of this frequency. Atoms in a crystal are arranged in a regular structure. X-rays penetrate the crystal and are scattered by atoms in different layers of the crystal lattice. The scattering angles of X-rays are also described by Bragg's law. This law enables us to investigate atomic spacing in the structure of crystals or to measure the wavelength of X-rays. In the same way, we have also been able to determine the wavelength of neutrons scattered by crystals. A pulsed air jet directed at the stationary water surface generates waves which travel outward at constant velocity. As long as the source has a fixed position relative to the medium, the wave pattern is a set of spreading concentric circles. As the source moves through the medium, each wave is generated at a different spot and spreads about a different origin. Ahead of the moving source, the wave fronts are closer together. Behind the moving source, they are further apart. Here the source is moving at constant velocity when it enters the picture. The distance between successive crests propagated to the right is shorter than the normal wavelength, and the distance between crests traveling to the left is longer. In a given time, many more waves will pass an observer in position A than will pass an observer in position B. A higher frequency is detected at A than at B. This phenomenon is the Doppler effect. If these were sound waves, the pitch would be high as the source approached a listener and low as it receded. If they were light waves, there would be a corresponding shift in color toward the violet with the source approaching, or toward the red with the source receding. Astronomers point to the red shift in the starlight from distant galaxies as evidence that we are living in an expanding universe. Now the velocity of the source is greater, about 2/3 that of the waves. The source velocity has been increased so that it is close to the wave velocity. You can see that the source almost overtakes the wave fronts. The ratio of the source velocity to the wave velocity is called the Mach number. If we were to increase the source velocity until it equaled the velocity of the waves, the situation would be described as Mach 1. Here the source travels slightly faster than the waves, and there is a strong disturbance building up at the source. Well beyond the velocity Mach 1, The source moves ahead of the advancing waves, and the envelopes of the reinforcing waves are two straight lines, each at an angle theta with the line of motion of the source. The source moves ahead of the expanding wave. The velocity of the wave and the velocity of the source determine the angle theta. Sine theta equals the ratio of the wave velocity to the source velocity. Each of these two lines is the locus of a strong wavefront, where the energy is concentrated, then carried outward by a shock wave advancing continuously in the wake of the source. An aircraft traveling faster than the speed of sound in air creates such a shock wave. It causes the sonic boom. Another familiar shock wave is the bow wave a ship sends through the water. In the same way, high-energy charged particles traveling through matter produce a shock wave of electromagnetic radiation called Cherenkov radiation.